Yeah, so welcome to our session on machine learning and applications. As far as I know, all the speakers are present. The talks should be 15 minutes. I will make some sounds when we are close to the end, and there will be a Q&A session at the end of the session, Q&A session for all of the 4 speakers, unless one of you ends very much early. So for now, I want to welcome Jędrzej Świeżewski, probably wrongly pronounced. I saw you on the chat. I would ask you to share your screen and then start with your presentation on FastAI in our preserving wildlife with computer vision. Thank you very much in advance, Jędrzej. And I stop sharing now. No. Stop video now. Good. Very good.
Yes, so I'm turning my camera off and sharing my.
Excellent.
So you should be seeing my slides now.
We do. Excellent.
Okay. So hello everyone and welcome. My name is indeed Jędrzej Świeżewski. I work as a data scientist at Epsilon Data Science, and professionally my main focus is on computer vision. I have an academic background in theoretical physics, and personally I'm a fan of everything related to winter. And because of that, I need winters to happen, and hence my interest in ecology, and in particular in wildlife conservation. So today, I will be first telling you a bit about how artificial intelligence, or in particular computer vision, can assist in wildlife conservation efforts. Then I will argue for FastAI, which is a Pythonic library which is exceptionally good in computer vision, in achieving outstanding performance and doing it fast. And lastly, I will explain myself as to why am I telling you this in an R conference. So I will show you that you can make use of the advancements which are offered by FastAI from within your R environment. So let's jump right into it. One of the recent advancements in wildlife conservation is the introduction of camera traps. So in the second image from the left, you see an example of a camera trap installed on a tree in Central Africa. And then this device is typically having a heat sensor inside, and then it's meant to take a picture of an animal passing in front of it whenever the heat sensor triggers the camera. With such tools, vast and fascinating data sets are collected. So the other 3 images are examples of images taken by such camera traps. I want to point your attention to the image on the right, which shows an elusive African golden cat, which is the least studied wild cat in Africa. So the message here is that with the introduction of those camera traps, we obtain fascinating data sets which contain real gems inside. But one of the key problems with using this technology is that in reality, most of the data sets look like this. So they're just empty. They're images of leaves moving in front of the camera, or just the camera being triggered by some unknown phenomenon. Anyway, large majority of the data set is just empty images. And this is a problem because the precious time of the wildlife conservation efforts is now spent in sorting through images. So they collect thousands of images and sometimes spend days or even weeks sorting through images to first filter out all the images which are completely empty and useless for them. And only after they get the images with the animals selected, then they can actually process them, for example, using the presence of different species of animals as proxies for assessing the health of the local ecosystem. So this is very precious knowledge, but it can only be obtained after this mundane work of sorting through images. So artificial intelligence or computer vision could vastly improve the workflow of conservationists if we can build models that can successfully identify animals in those images. And I want to show you 2 examples of cases where where we have achieved that. So the first one comes from Hakuna Matata competition, which was organized earlier this year by Driven Data. And in this competition, participants were given a huge data set of over 6 million images from African savannas. An example you can see on the left. Most of the images consisted of, half of them was taken by the grass of the savanna, half by the sky, and then there were some animals here and there. And the task was to, of course, identify correctly those animals. Now, we decided when joining this competition not to go for the typical approach in such competitions. So we didn't want to build a huge ensemble of complicated models which would have all sophisticated types of tweaks here and there to obtain just a slightly better result. But rather, we decided to take the robust approach. So we've actually based our solution on a single neural network architecture. And then with just a few tweaks, we've managed to achieve the 5th place out of 800 participants. Now, happy with this result, we decided to test our approach in a real-life wildlife conservation use case. So we've joined the efforts of conservationists from University of Stirling and also collaborated with a National Parks Agency in Gabon. And there we worked with a data set of over 1 million images, but this time taken in African forests. And it turns out that our approach was very successful. It gave us very promising results, which will help to advance wildlife conservation efforts by automating large parts of the effort. And then the results will be soon announced in a paper. But what I want to highlight here is that the two cases are actually very different. Because in the top one, the images were taken on the savanna, and in the bottom one, they were taken in the forest. And that, in fact, constitutes a very huge difference. And I would like to take you a bit along the journey. So here are two examples of images from the data sets. So on the left, you see an image from an African forest. And then our model was with high certainty telling us that it sees an Nkulengu bird in this image. So can you see the bird in this image? Well, we could not, but because the model was so certain, I looked very closely and then eventually spotted the bird here. So you see that its beak is turned toward the left, it's hidden behind some branches and some leaves, and actually at the bottom of the shape, of the blue shape, you can see that there is a piece of the red, characteristic red leg of this bird also visible. So this shows you how hard the task of sorting through those images manually is. So the conservationists need to look through thousands of such images and quickly identify what type of the animal is in such an image. Another example is shown on the right. And here you see something that we've noticed when dealing with those models, that of course some of the images were taken at night. So the cameras were triggered at night. And then our models in some of the cases kept telling us that there are animals in the image. So in this one, the model is highly certain that there is an elephant somewhere in this image. Obviously, it's impossible to see, but I've decided to dig deeper into that, and with some simple tweaks of brightness level in this image, just with some simple software for tweaking images, you can see that in fact there are some tiny differences in pixel intensities in the middle, which actually show you that there was an elephant family walking in front of the camera. So this shows that those models that we've built are actually performing in an outstanding fashion. And then we were able to build them very fast and in taking this robust approach, so in a rather simple and understandable setting. And that was made possible because we've used the FastAI library that I've mentioned before. So let's now shift gears, and I will introduce you to the library called FastAI, which is a wrapper on PyTorch, which is a framework for deep learning in Python. And I would like to argue that not only with FastAI, as you have seen, we can produce those outstanding results or state-of-the-art results, but we can also do that very fast. So now let me take you to an R notebook, which shows you how quick the training is of a simple model. So I will be using the reticulate package to interface between the R kernel and the Python kernel. The Python kernel is an environment that I've built using Anaconda its entire configuration is actually in those few lines. So it's just, I'm just installing PyTorch, FastAI, and a helper library for dealing with images. And then we execute the Python code from within the R kernel using the reticulate function pyrunstring. So here we start by importing the library, FastAI Vision. Then we prepare the data. So here we basically need to have a data frame which identifies images, tells FastAI from what category they come and whether they are in validation set or in the training set. So for this use case, I will be using a simple data set of 80 images of crocuses, 80 images of lily valleys, and 80 images of daisies. And here you see example images from this data set. And we'll be building a classifier in FastAI, which will be able to identify which type of flower we're looking at. So let's do that. I should also say that in this part, we are actually building a data bunch. So it's just an object that FastAI uses to represent the data, to basically identify where the images are, what they are, and which data set they come from, so which sub-data set they come from. So we've done that. We have the data bunch. Now we need to construct a learner object, which basically holds a model. So it's constructed from this data bunch that I've created. We are using a squeeze-net architecture, which is a very small and fast architecture, allowing to produce decent results and exceptional for such a size of model. And I'm using this because it allows me to train on my laptop without the access of a GPU. It's just a bit too long to show you live the training in this demonstration, but because it takes a few minutes, but still it's definitely workable to experiment. And then I define that I'm monitoring accuracy during training. Now we are using here a tool from FastAI which allows to produce this graph, which basically, with some heuristics, allows you to pick the right learning rate, which is optimal for that data set and that model at this stage of training. And then we run the key line, which is this one, which allows us to fit the model to the data with just a few parameters. So how long it should train and what should the learning rate be. Now here we see that I'm using a function called fit1cycle, which exemplifies that FastAI has incorporated the latest developments in the field of computer vision, namely in this case, one-cycle policy training. Now we see that the model is training. In a few minutes, we get a model which has 92% accuracy, which is good. This is a rather simple data set. So even such a small model can fit it very nicely. And we see that we can plot the results. Now, the key message here is that it was quick to build the first model. Now, can we do it from the R level? Well, the answer to that question is in this notebook, where I will again use reticulate, but this time all the objects will be actually on the R level. So everything will be represented by an R object. Again, we are configuring the framework, or sorry, the kernel, and then we're importing the library to an R object called FastAI. We're building an R data frame, which has all the information necessary for FastAI to train. Next, we're forming a data bunch, but this variable data is now an R variable holding the data bunch that will be served to FastAI. We define an R object learn, which holds the model, the learner. And then, using the same trick, we find the learning rate, and we fit the function. Fit the model to the data. Now, we've obtained a slightly higher accuracy, which is a definite proof that R is better than Python. But the key message from this notebook is that you can do the experimentation, you can do the training, not leaving your R framework. So that is all very nice. But let me show you another use case, which comes in the shape of the following situation. So let's imagine that you've been told that there is a great FastAI model that you would like to use in your application, which runs in R. Can you actually make use of it? And the answer to that is yes. So
time is over. So try to wrap up in a
minute. Here I'm just showing that you can actually load the model from FastAI, entirely trained in Python, into an R session. you can execute classification on R, within R, and using all the type of data handling and processing that you want from R, you can actually visualize the results of classification from the FastAI model in R. So you can embed it in, for example, your R Shiny dashboard, if that's what you're after. So the take-home message that I wanted to share with you is that AI is applicable. We see concrete applications in important subjects. FastAI is a very cool library that is fast and producing state-of-the-art results, and you can make use of it, not leaving your comfortable R sofa. Thank you very much. And if you have any questions or comments, please feel free to reach out or ask during the Q&A session. Thank you.
Thank you very much, Jędrzej. Indeed, you can also answer the question to the chat using the syntax that was given at the speaker and then the #Q to S. Our next speaker, or two speakers, are Luca Torriani and Ilaria Sartori on Manifoldgstat, an R package for spatial stats in manifold data. Welcome, Luca and Ilaria. We see you already on video, and I assume you will take over now.
Good morning, everybody.
Good morning, everybody. Hi.
We turn off
And you will.
Okay.
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 We can see it. It's good.
Good morning, everybody. Today, my colleague Ilaria and me, we are going to present the problem of prediction of spatially dependent manifold value data. Such a problem can be encountered in several fields like meteorology, for example, to analyze the covariance between temperature and pressure in a specific region, mobility, to study the traffic of vehicles in a city, or even medicine, for instance, when studying the diffusion of water in the brain. First of all, we introduce the problem we dealt with, followed by some basic concept of differential geometry that we exploited to develop our method. Then we show three different methods to perform the analysis and how they have been implemented in the R package Manifoldgstat. As anticipated, the problem we dealt with is the Kriging prediction of spatially dependent manifold value data. Thus, our setting consists in a geographical domain D, which is a rectangle in the picture, and location Si, identified via x, y coordinates, where n values of a stochastic process Ks, valued in a manifold, have been observed. And finally, one or more location S0 in black in the picture, where the value of the process is unknown and has to be predicted. In particular, we focused our attention on the case in which Ks is a symmetric positive definite matrix, represented as ellipses in the picture, and the domain D is a rectangle. Therefore, the manifold of interest is the one of symmetric positive definite matrices, which is commonly referred to as PDP, where P is the dimension of the matrices. Unfortunately, this is not a vector space. For instance, for P equal 2, it is a cone, and this means that common linear models cannot be applied. In order to overcome this problem, as shown in the picture, the manifold can be approximated through a tangent plane. In our case, M is the PDP, and as a consequence, TXM is the space of symmetric matrices, which is indicated as SymP. In order to move from the manifold to the tangent space and vice versa, we will define the logarithmic and the exponential function with the capital letter E and L. To this end, PDP has to be equipped with an inner product. Commonly, Frobenius product is used with the matrices. However, with such an inner product, our manifold would be plain, but with an incomplete metric. This means that matrices with null or infinite eigenvalues would have an infinite distance from a symmetric positive definite matrix. For this reason, we chose the Frobenius scaled product, reported in the slide, in order to endow the manifold with a complete metric. This choice guarantees that there exists only one geodetic connecting two matrices in PDP. The geodetic is the extension of the concept of straight line to manifold. Thus, given 2 points on the manifold, it is the curve which describes, at least locally, the shortest path between them. The geodetic concept is fundamental since, thanks to that, the exponential and the logarithmic maps can be defined, a distance on the manifold can be induced, and finally, exploiting the induced distance, the concept of intrinsic mean can be introduced. Namely, given a set of data on the manifold, the intrinsic mean, mu, is the point which minimizes the mean squared distance. As anticipated, we now present 3 different methods to perform Kriging prediction on data on PDP. The first 2 are already in the existing literature, while the third one represents our innovative contribution. The first method proposed is also the core of the other 2 approaches. We call it global model since it is built using all the data together, but this will be clearer in a few minutes. The model assumes that in each location S, the observed stochastic process is defined as the exponential map through a constant tangent point psi of the sum of a deterministic drift ms and the stochastic residual delta s. Moreover, we assume that the deterministic drift is given by a linear model and the residual are second-order stationary. Summing up, we obtain the expression shown at the bottom of the slide.
Here instead, we can see the entire algorithm. Without going into much details, it is just worth noting that the linear model on the tangent space is fitted through generalized least square, where the weights are computed taking into account the spatial dependence of the data, captured with via variogram of the residuals. The prediction is eventually given projecting on the manifold the sum of the deterministic term and the simple Kriging interpolation of the residuals. The assumption of stationarity across the whole domain is the main limit for this approach, since it is usually not satisfied, like for the field in the bottom right picture. So the second method aims at solving this problem by dividing the geographical domain into k smaller subregions through Voronoi tessellation, and applying in each one of these the global model described a few minutes ago. This algorithm, based on a divide et impera strategy, is called random domain decomposition, RDD, and requires to assume only local stationarity. Since the partition of the domain is random, the procedure is repeated many times, let's say b times, and then the results are aggregated. So, as shown in the graphical schema, at each repetition, we obtain a prediction for the value in S0, and then the final result is computed as the intrinsic mean of these values. The problem underlying this procedure is that we are dividing the analysis into multiple local analyses, and as a consequence, besides the computational issue, each time we only use a small portion of the information. Thus, the third method tries to keep the idea of partitioning the domain in order to deal also with non-stationary fields, but then combine all this analysis into a global one. Unfortunately, to this end, we need to connect data which lie on different tangent spaces. The solution to this problem is given by the differential geometry concept of parallel transport. The formal definition is pretty complex since it's based on the notion of affine connection. However, the intuition behind it is quite easy. Indeed, the idea is that to parallelly transport a vector along a curve, you have to keep it pointing in the same direction as it moves. Luckily for PDP, there exists an explicit formula to do it. So let's now see how this innovative method, referred to as mixed RDD, applies this concept. The procedure still exploits RDD, but only to define for each location a fictitious tangent point. This point represents the mean local value of the field, but it's not used to build a tangent plane where to fit the model. It is only the starting point to parallelly transport that datum on a common vector space. As a common space where to project all the data and then run a global model analysis, we chose the space tangent to the manifold in the identity matrix. In these slides, there are the details of what I try to briefly summarize. It is worth underlining that this method performs a global analysis, but without losing the information about local patterns, which is captured by the field of fictitious tangent points. So these all three methods have been implemented in an R package available on GitHub. Since these approaches are computationally expensive, the core of the algorithms, namely the global model, has been developed in C++ in order to maximize the efficiency. When the user calls a method of the package, an R intermediate function is invoked, and exploiting the RCPP library, it in turn calls a C++ routine. And now we know you have all been craving for some details about the code, so here they are. For example, it's worth noting that we use the two design patterns, template factories and proxies, to handle runtime inputs and granting code extendability. Moreover, we also implemented in C++ the Gauss-Newton algorithm used to solve the optimization problem that determines the parameters of the variogram. All the mathematical details are shown here in the slides. Now, some other juicy technical remarks, like the fact that to handle matrices and vectors in C++, we use the eigen library, while to save memory, we widely took advantage of shared pointers. These tricks, along with many others, allowed us to improve the efficiency of our first entirely R-written algorithm by a factor of 1400, as shown in the figure. We will now just give a first glance to the results of a simulation study that we conducted to compare the three methods on different settings. So without delving into the details, they just show that on stationary data, mixed RDD has an accuracy comparable to the one of global model, while on non-stationary data, it can have even better performances than full RDD. Of course, it comes with the price of an additional computational effort with regards to the global model, but it's extremely reduced if compared to full RDD. So this will be it. Thank you all for the attention, and special thanks to everyone involved in the organization of e-Rum2020.
Well, thank you very much, Luca and Ilaria. You kept to the time, even saved a few minutes. Please, everybody ask questions to them on the chat with the usual syntax at, for instance, Ilaria Sartori, and then #Q2S, 3 letters, and formulate your questions. So they will all be collected, and in the end we can see the questions. Our next speaker now, almost in time, will be Jakob Dambon. He's actually from Zurich and Lucerne, a PhD student. I know him because he was in the same institution as I am. Welcome, Jakob, to your talk on varycoef, modeling spatially varying coefficients. And I will turn off my sound now, and you can turn.
Okay, so can you hear me?
Yes, we can hear you. You should then turn off your video. Perfect.
Okay, great. So thanks for having me. I will be presenting my work on spatially varying coefficients as part of my PhD research, and at the University of Zurich and the Lucerne University of Applied Sciences and Arts. And with my supervisors, Fabio Sigris and Reinhard Fuhrer, we then took what we did on the methodology part and implemented it in an R package called varycoef. And maybe you have some data lying around that you never analyzed in this fashion before. So let me give you an example of what we are after. So the example is the following. Maybe some of you already know it, but the MUSE data is one of the most popular spatial data in spatial statistics, very well studied. And it consists of some heavy metal concentration along a river. So these are the columns here: cadmium, copper, and so on. And we have some further information like the elevation and the distance to the river. And now, if I say I want to have a model that predicts the level of cadmium depending on elevation and the distance, we all know the linear regression model, where we take the data set in R, for example, with the LM function, and apply the here I apply a log on the cadmium levels and have my covariates, elevation, and distance. And with this, I receive then the coefficients and can use them or the prediction function to give prediction at any site. However, there's one particular thing which I want to show you now. The first two columns of the data sets have the coordinates where the values were sampled. And as you can see, there are some spatial clustering now here for the logarithm of cadmium. The higher values are with this yellowish color, and there are some clusterings with the level of cadmium that even the covariates like elevation and distance to the river cannot model. So this opens the door to spatial statistics. In spatial statistics, we have a classical geostatistical model where the first part is very much the same as the linear model with the covariates. Now we refer to this to this beta part, to the sum of the betas here as the external drift, and we put a focus on the Z, and the Z captures then the spatial relationship. So and all of this is then underlying the first law of geography by Tobler, and here he stated that everything is related to everything else, but near things are more related than distant things. So what we are trying to do in spatial statistics is to model these Z, and there are some methodologies on how to do so. For instance, you can use splines or Gaussian processes, and I listed a very short list. There are many more, so you can take a look at the task view on CRAN regarding spatial data. But yeah, there are some nice references there. And for instance, this Gaussian processes are very well known to model dependent data in a very nice manner. So we take this as an inspiration and then apply it to spatially, and then define the spatially varying coefficient model. So the idea is the following: each coefficient has now some spatial structure. And you can see the model here looks like a linear model, but now for spatially varying coefficient, you can see that each each beta is depending on a location. So this has some advantages and disadvantages. So some advantages is that the model is not a black box, and even if you give me a one location, I can the spatial variant coefficient model reduces then to a simple linear model. And with this, this also comes some high flexibility. On the other hand, it is computational intensive, depending on how you define the spatial variant coefficients. And of course, you need some moderate size of data, so you shouldn't run these on a couple of dozens or a couple of dozens of observations. So I show you now the existing methodologies for this for these spatial variant coefficients models, and in particular, these are the ones that scale to large data. I will come to what I mean by this in a couple of slides, but now I want to show you the most prominent ones. Geographically weighted regression. There are a couple of packages on CRAN. And for example, another approximation via Gaussian Markov random fields, which you then can use running inla. Our research resulted in a simple maximum likelihood estimation and is now on CRAN, and the implementation of this in a statistical software is now available on CRAN, namely in the varycoef package. So the varycoef package models the spatial variant coefficient as Gaussian processes, and it was specifically designed to work with large data. So we apply two things here. On the one side, we have the covariance tapering, and covariance tapering introduces sparse matrices, which are then beneficial because, of course, they reduce the computation time within an optimization process. The maximum likelihood estimation is a numeric optimization in our case, and this optimization is also parallelized. So the classic optimization function in R is now available as with parallelization. And if you don't know it, you should really check it out. It's really nice. And I was talking about large data, so this is not the same. So I should say in spatial statistic, large data is already regarded if we have more than tens of thousands of observations and more than dozens of observations. So with this regard, varycoef scales to large data, so to say. And once a model is fitted, we get an object of class SVC MLE, like an LM object, and then we can apply the classical methods for this object like you would have in an LM. For example, you can take the mean coefficients, you can look at the fitted values, you can use the predict function to give new predictions for new locations or for new covariates, and summary functions. So this is the current state of implementation of methods. Okay, so how does this now look like in the code? So for modeling using varycoef, the basics are quite simple. There are lots of details you can change, but parameters you can change. But to give you an overview, you need a design matrix, which is the first line of code. Then you need some kind of dependency measures, and for example, with the first law of geography, we need some dependency structure. And in spatial statistics, we usually get this one out of a 2-column matrix indicating the locations in a particular coordinate reference system. So like the first 2 columns in the MUSE data set, which are the sample locations. Then there's a control parameter, a control function, which controls the optimization process. You have to set an initial value. You can set lower and upper bounds for the parameters if you want to. We implemented a procedure that works on a profile likelihood. So this speeds up things even more because it reduces the dimension of the parameter space. And once all of these are defined, you can then run the maximum likelihood estimation using the SVC_MLE function. So I give you now an example which we also considered as an application to real-world data in the publication, in the preprint. This one comes from real estate data. We have some apartment, we want to do price prediction for apartments in Switzerland. There we looked at roughly 15,000 observations for a training data set, and we tried to model 8 spatially varying coefficients. So the next slide is the result of one of these models. It is a selection of the estimated SVC. So these are the 4 ones which are have the most of the spatial structure. Maybe I can zoom even into so you can see more. For example, the intercept is this SVC for the intercept is given in this panel here, and it can then be translated to the mean pricing. And you can see that around the metropolitan areas of Zurich and Geneva, the mean pricing level is higher than, say, in the rural areas of Switzerland, like to the northeast, northwest, and the alpine regions of Switzerland. Or, so this panel you could also obtain via classic geostatistical methods. This panel here on the right shows then the spatial variance coefficient for the area, the log area of the apartment. And the price, this can then be interpreted as the price per square meter. And, yeah, and what you can see again is that in the metropolitan areas, the price per square meter is higher than in more rural areas. And the other ones, I will skip them. I think the idea should be clear now. Yeah, so this was a really nice application, but of course, you're never done with such a package. So currently, we are, or one idea would be for future work would be to implement more covariance functions. These define then the Gaussian processes. And currently, the dependency measures is purely on the locations, which is 2 columns. We want to implement higher dimensional domains, so you can use 3 or 4 dimensional. And now you might ask why? Because you could implement something like a time or space-time to do spatial temporal statistics, or use something even like a socioeconomic status or some other dependency measures to model these spatial variance coefficients. And currently, we are also working on spatial variance coefficient selection, which is similar to an elastic net, lasso, if you're familiar with those. And here we want to try to answer which SVCs or covariates do I need. So with this, I would say thanks for having me, and yeah.
Thank you, Jakob. Thank you, the audience. Please ask questions in the chat, and we will switch to the last speaker, Mikkel Meyer Andersen. He will present computer algebra systems in R, something which is quite interesting to myself. So welcome, Mikkel. Can you quickly show yourself before switching?
Thank you very much. I hope you can hear me.
Yes, and we can see
Good.
you.
Say hello. Welcome to everybody, and thanks for joining us for this session as well as the conference. I will try to share my screen and hope that it works.
Yeah.
Good. And works. I will switch off my video like that.
Perfect.
Good. Well, first of all, thank you very much for coming. I will, as Martin said, be talking about computer algebra systems in R, namely the Caracas and R-Yakas packages. My name is Mikkel Meyer Andersen, and this is joint work together with Søren Højsgaard. So, as you've already heard, please ask a question in the Hop-in session chat. Tag my name, Mikkel Meyer Andersen, and then the hashtag Q2S, and then the question. And then I guess we'll have time for that during the Q&A session. So first of all, I'll start with backgrounds for these two packages. So R-Yakas is a package that is based on the Yakas, yet another computer algebra system that works on multiple platforms and is a program on its own, just like Mabel or whatever you might know. It's open source. In around 2007, it came on CRAN by the authors you see here. And in 2017, I became the maintainer. There were some problems about XML communication between the Yakas process and then the R package itself. And actually, we ended up deleting that intermediate communication so that the package communicated with Yakas directly and not using any XML. And we published a Journal of Open Source Software paper on that in 2019. Here I just gave you some links for that package. It's on CRAN. The stable version and the development version you can see on GitHub. And you can also see online documentation made by Package Down. The Caracas, on the other hand, is based on SymPy, which is a very large computer algebra system for Python. So what we did was to put that into the package and then use reticulate to communicate with the library. The main purpose of Caracas is also that this should not be visible by the users. The users should not be able to know any Python in order to use the library. They should know R, and that should be it. So our aim was more or less to translate SymPy objects to R back and forth and make them sort of feel and look like R objects. The name may seem a bit weird or strange, but there's a reason behind it, and that is that cara, that's face in Spanish. So it's sort of an interface to CAS systems. And we started this project in 2019, Søren and I, and it's supported by a grant from the R Consortium. And here I also give some links. Again, it's on CRAN, but the development version is also on GitHub, and there's online documentation. You may note here that it's actually inside a GitHub organization. So if you go to that RCAS organization on GitHub, you will see both repositories as well as some other ones. And then you probably ask, what is the difference between these two packages? Well, they have actually their pros and cons. So for example, R-Yakas is tight two-way integration. So Yakas is bundled with the package and the communication is back and forth. And it's actually fairly good because Yakas itself can translate its code to R code. There's a function in Yakas that does that. So that's pretty good. You can also extend the language, so it's actually a programming language in itself. So if it does not recognize a particular infinite series, you can actually implement that rule yourself and exploit that. On the other hand, it is not as feature-rich as SymPy is. SymPy is very large, many developers, lots of effort going into that. On the other hand, the communication is a bit more, it has to go via reticulate and go back and forth. But our goal is, of course, to make that invisible for the user. Both works by creating these symbols or symbolic variables. The syntax is different between the two libraries, but the main idea is to create a symbol and then use RS3 generics to make it invisible for the user. In this talk, I'll focus on Caracas, and we'll also focus on that in the future development of the software. So I will show a few examples here. First of all, to get started, you have to, of course, to install the package, either the stable one or the development version. And then you need, of course, Python in your machine in order to install reticulate. And what I'll show here is sort of a small mixture of calculus, linear algebra, and a bit about solving equations as well. So the syntax is that you create a symbol. So here I create X and I create Y, and then I can use my normal R syntax to create an equation. And then I can, for example, take the derivative of that equation with respect to X here. And then I print the output. So that's, of course, 2x plus 3. I can also, for example, calculate the Hessian. So that's saved into H. So that's not printed right now, or could print it just like I did before. I can also convert it to a character if I prefer that, but I can also make this tech code out of it. So this equation down here is made with that small piece of code. And of course, you would try to evaluate the Hessian, for example, in a critical point or something like that. So what we do is to convert a Caracas object to an R expression by that function called as_R. Then we are returned an R expression, and we evaluate that for some values of our variables. There are some functions. So there is, for example, summation, integration, and limit. I'll show you now the sum function, and we chose to call it sumf because we sum a function, whereas in R we have the sum that sums a vector. And to avoid confusion, too much confusion at least, we call it sumf, summing a function. So we need to put in the function itself, the variable we sum over, and the limits. And then there is this doIt argument, and what it says or what controls it is whether the sum should be evaluated or we just set up the computations and then we can evaluate it afterwards. And I'll show you a brief example of that. So first we create a symbol k, and we sum k for k equals 0 to n, and we'll not do the computation yet. What we'll do instead is to create another variable where we do the computations. And this enables us, for example, to do something like that. So we, in tech, write the computation here, or the sum that we haven't computed yet, and then we equal to that to what we have computed. And there is a simplify function in Caracas as well that tries to simplify an expression, and I'll show you that again in a bit. Integrals is called intf, again along the same lines, to integrate a function. Same syntax. I'll just skip this a bit quick because you can see it for yourself, but I wanted to include this so that you had the whole story. The same with limits, limf, so we take the limit of a function. Same syntax. About solving equations, there are two workhorses. So sorry about that. So there are two workhorses. One of them is to solve a linear system of equations, and the other one is to solve a system of nonlinear equations. So I'll first demonstrate a quick example with this system of equations. So the syntax is that we make a left-hand side with the equations. So here I make the 3xy minus y, and then the x, and then the right-hand side with minus 5x, and then y plus 4. And then I solve that system. So I call my function solve system, left-hand side, right-hand side, and what variables I want to solve it for. And then I print the solution. And as you see here, we actually get two solutions with some values. And of course, I may want to extract that particular element. So in the first solution, I may want to extract the x variable, and I do that subsetting that solution with the first solution, and then taking my x variable, and I get out a Caracas expression. And again, I can convert that to a numerical value with this as-r function. In linear algebra, we often have some matrix of sorts, and that can be a bit cumbersome to construct them using c-bind and r-bind, as I just showed you. So we also have a function called as-symbol. And what it does is try to convert an r object to some Caracas symbol. So for example, if I want to create a matrix that looks like this, 2, 1 for x, then that's a character matrix, sorry. And then it's converted to a symbol like that. And what we get out is actually a symbolic matrix. And that we can transpose, for example, but we can also subscript elements and rows and columns and all that, as we are used to with R matrices. There are some special functions like determinant. We can take the inverse, which is a special case of the solved linear system that I'll show you in a bit. And again, as I mentioned before, we can simplify the expression. So you see here that it factorizes a 2, for example, in the denominator of the first element here in the matrix. And here's just a small example if you don't want to invert the matrix by hand, but if you actually have a y, so A is known to us, and then we imagine that y is known to us. We do not know what b is. So the game here is to find b. So we set up what y, the vector is, and then we solve the system for a and y to find b. And then this is our result, and we simplify that and see that we obtain exactly b. So that's a short example of how to use that solve lin function. And now I will go to a bit more elaborate example with the multinomial likelihood. That's an example that is often used in introstats courses, for example. So say that we have a multinomial observation in 3 categories. Then we write up the likelihood for the parameters p, given the observation counts y, and we get that it is proportional to that expression here. If we then take the log, we'll get this lowercase l function of p. So that's the log likelihood, or proportional to the log likelihood at least. And I write up a function g, and the reason is that g is a constraint. So we need that g should be 0 because we need these probabilities to sum to 1. So we actually have a constrained optimization problem, and we, using Lagrange multipliers, we convert that to an unconstrained problem. And that's with this capital L you see here. And the way we write that in Caracas is that instead of calling it lambda, we call it A, and we say that we have a P vector here. So again, I have a vector, character vector, and I convert that with the as symbol, do the same with Y, and then I create my A. I could have written symbol here instead. And as you see, it actually generalizes. So if I want to have 4 or 5 categories, it would be the same, because you see the L log likelihood here is just vectorized as we're used to in R. So we have our capital L function here, and that's the one we want to do critical points for. And you may note that we want to maximize that lowercase l, and we put a minus in front of it. So we actually want to minimize our capital L. So what we'll do is to take the gradient of L because we want to find critical points, and we take that. If I do not put in a right-hand sign for this solves this, it finds root. Roots are set equal to 0. So I want to find the zeros for the gradient for variables P and A, and that's my solution. So that's actually our maximum likelihood estimates here. And as we know, where P1 equals Y1 divided by the sum. And you could, of course, if you wanted to, you could investigate the Hessian, for example. Last small example is one-way ANOVA. That's also a typical example in introstats courses. So the game is here that we have 3 groups, and in each group we have 2 observations. So this is some R syntax to actually just find the design matrix. So the first 2 observations belonging to group 1 is the first 2 rows here, and then we have 2 observations belonging to group 2. So that's a dummy variable, that second column here, and the last 2 belongs to group 3, the last column. Then what we want to do is try to see how that sort of textbook formula, how that works. So if we have to estimate beta hat, then of course that's not how you would do it numerically. That would give you problems, but analytically, this is in principle how we do it. So you take the transpose of x times x, invert that, and then multiply that to x transpose y. And if you do that, we'll also see here that the estimate of beta 0, so the intercept in the model, is just the average in group 1. Beta 1, the effect of the contrast of going from group 1 to group 2 is actually the difference between the averages in group 1 and 2, and the same for the last one here. So this actually, using computer algebra, shows how the linear algebra works. And Martin was coughing, I guess, and I'm actually done with my slides as well.
Yeah, I wasn't even coughing yet. I saw that. Yeah, thank you very much, Mikkel Meyer. That was also a very nice presentation. So we are at the end of the 4 presentations. I would really like to thank all the 4 speakers. It was very interesting, very diverse too. And I hope we'll have a nice Q&A session now, which I have to check how to organize in detail, and I will get help from Massimiliano and others. So yeah, where are the questions? Massimiliano tells me they are somewhere, but I don't see where they are. Okay, I should try.
Martin, we have missed your video. Can you please ask to share again and come back for the Q&A session?
Okay.
Here
we are, everybody, and I also see all the other speakers. Perfect. But you could hear what I said, right? Okay. So the first question to the first speaker was, could these image lessons be useful for healthcare setting images such PET or CT, very important medical imaging situations?
Yeah, so I believe they can. We haven't done that ourselves, but I know that FastAI has a separate branch, so to speak, for medical data. I've linked in the chat a presentation by the creator of FastAI, Jeremy Howard, of the use of this part of the library. So definitely it can be used for that as well.
That's good. There was another question from Saint-Marie Vivier. Is your R notebook available in public repo regarding the flower example that you gave?
Yes, so also Nina Autopal asked for this. During the session, I have uploaded it to the GitHub repository that I've linked to in the chat. So okay. you can find it there.
Yeah, I don't know actually if the chat is saved. Can Massimiliano or somebody confirm that the chat is also available a little bit longer, or how can people get such links from the chat?
Still available, yeah. So you can click on it now.
Yeah, so it's available at least now. That's good. And people have to get it now before the session ends, probably. Yeah, so the other question. Oh no, sorry, I've switched down to. Yeah, I need to concentrate too here. The next question, you saw it yourself. What the advantage do we get in choosing FastAI instead of Keras and TensorFlow, which was the usual approach that people started using with R and R packages, reticulate, and so on?
Mm-hmm. Yeah, so that's a very good question. Indeed, there is obviously some competition between the two approaches. There are many arguments for one or for the other. I invite you to read up on that. But in my opinion, the main thing that I see about FastAI is that it's best for people who are not experts in machine learning and they still want to apply it to their use case. So I know of domain experts who were able to, of course, knowing some computer science or being, knowing how to code, they were able to basically follow the FastAI course, which I highly recommend, and then work on their own use case on their own. So basically, it has a very low threshold of entry. So that's for me the main advantage. Also, some of the latest developments in the field are first introduced in PyTorch and therefore available in FastAI, and only later come to TensorFlow, which might give you an edge.
Thank you. Follow-up question again from somebody, Vivier. Can you also do this whole thing like the flower example in our Markdown file, or even though it uses reticulate and so on? Or
I think so. Yeah, I think that's what I did.
Yeah. Okay. So you use regular R graphics, graphic devices, not the Python graphics, for instance. Yeah. Elisa Donati asked, could it also work to recognize color patterns within the same species, since you were classifying species,
yes,
flower species?
That's a very interesting question, and I think in principle, yes. And not the models directly. So the models I've used, the two of them I've shown or discussed, were meant to classify species, not within the species. I know of people who are looking at different animals within the same species and then trying to identify it. It is possible. The challenge there is that the characteristic needs to be visible. So, for example, I guess that it's relatively easy to do that for zebras, as long as the set that you're classifying is not too large. But it's going to be very hard for, I don't know, lions, which are not, the characteristics are very tiny. So you'll need high-resolution images of lions. So the information needs to be there, and therefore it's going to be harder. But it's worth a try, definitely.
Yeah. And the last question was from Massimiliano himself, our helper. Do you see any potential applications, cross-validate? Well, CV applications means the cross-validation, but also in the industrial oil and gas sector, for instance, for predicting maintenance field or. So,
yes, definitely. It's heavily used in such industries. One example use case is for defect detection. So you basically monitor the different elements of the pipes, for example, and then you try to look for cracks or different types of defects, and then you can detect them before they actually cause a disaster. So that's a huge benefit. There are other ways of using that. For example, you can identify the infrastructure just using satellite imagery combined with computer vision. So definitely there's a lot of room for using computer vision in industries like that, and it's being outrolled right now, I think. So it's not in the phase of being used by everyone. It's more in the kind of, as a field, it's more in the POC phase, I would say.
Thank you. Yeah, so we have to go to other talks. Thank you again for your talk and answering. Luca and Ilaria didn't yet get questions on the chat on their manifold fitting package, so to speak. I don't know if there are new questions. I had a question to your example, where your example was having ellipsoids, so to speak, ellipses. So how was that motivated? What real application is behind that?
Well, can you hear me?
Yeah.
Yeah. So, well, ellipses are just useful representation for matrices which are 2D dimensional. So in that case, we had this random field with values in PD2. So these matrices that were symmetric, positive, definite, and that we represented on this rectangle as ellipses in different locations. In the specifics, the use case we used was for covariance matrices between temperature and pressure. And another possible application, as we said, could be the diffusion tensors. So for water, for example, for brain imaging, or for other kinds of diffusion, even mobility, and as we can see, or other kind of diffusion analysis.
Okay, so where you would really kind of observe such covariance matrices as your data, so or as second level data.
Exactly.
Yeah, thank you. Yeah, I don't know if anybody has seen any other questions, or one of the other speakers who may speak. Otherwise, we have to go ahead to the third talk. Sorry. So there are several questions. The first from Martin Zerwek to Jakob Dambon and his varycoef models. He wasn't clear about the format for the init parameter, so that was very specific to one slide, but that was our code. I remember it.
Yeah. So each of the spatial variant coefficients is modeled by a Gaussian process, and this one takes the covariance function, and the covariance function itself relies on a couple of parameters. So currently there are two parameters, like the range and the scale. I didn't go into the detail here because it's a little bit technical, and it would be useful to have some background information in spatial statistics or Gaussian processes. But basically for each Gaussian process that you define, you need to provide initial values for the parameters. And usually the ones that I found out to be the best fitting ones are similar to the ones that you get from a spatial statistics application. But if I think that going further into detail would be would take too much time, and maybe Martin and I can meet up afterwards.
Okay.
To discuss details.
Thank you. There are two questions that are similar, one from Polina Korowska and from Nina Otopal, and both are about the sample size that are typical, or you mentioned in the beginning that you cannot use really small sample sizes for these varying coefficient, spatial varying coefficient models. And then, so she's asking, are you really needing 10,000 of observations? And then Nina Otopal is asking, and what about if you have 150,000? Does it still work? Is it still feasible? Or maybe you can generalize these questions and answer something.
Okay. So it has to be a moderate size. So I think I read a publication about who stated like at least 600 or something like this. So the model becomes unstable, so to say, below this. So this data set moves, it has too few, so for application here. It was a little bit unfortunate from my side to stay greater than 10,000. I wanted to express that it's feasible to be applied to more than 10,000. So we have this covariance tapering, which allows us to do this. It cuts the dependency at a specific predefined distance, and this basically reduces the computational load to a state where you are able to solve it. So it gives you a little bit of a bias on one hand side, but then the computational times are reduced. So I didn't try it out with 150,000 observations. You would have to taper quite aggressively, I would assume, but it's worth a shot. Currently, with the optimization parallelized and like a model with 3,000 observation runs a couple of hours. It's still an intensive task to do. And I think our models with 15,000, and we are now also for the revision, we are now also timing the computational time. So yeah.
Thank you. Yeah, that was another question about from Britta Welten about the covariance functions that you were thinking about. That one question, and the other was about memory usage, and if you could go away from linear models, for instance, to classification, binary classification, or others. So there are several questions. What covariance functions are possible, and how much is the memory usage? Maybe you can answer these first.
So covariance functions, we currently have the exponential covariance function, which has then 2 parameters, and a spherical covariance function, also with 2 parameters. You could also think about optimizing over like something like the smoothness of the optimization of the covariance function, like in the Matern class covariance functions. And there we would like to implement like with smoothness 3.5, 5.5, and so on. This would be the next steps. And then with regarding to time, there are also some possibilities, but we haven't looked into this yet. The second question was with the memory use. So we are fortunate enough at the University of Zurich to have servers with quite a bit of memory. So there we haven't had any bottlenecks.
But did you measure the memory?
No, for the application with 15,000 observations, a classical working like a working station grade computer, so like 32 gigs of RAMs or something like this, which is nowadays quite feasible. It's working with this. So because the dimension of the covariance function is solely by the number of observations and not the number of spatial varying coefficients.
Okay, and there's a last question before we switch to the last talk, namely how much faster is using OptimParallel and your method, how much faster is this compared to GW model, the one model you mentioned initially, the Gaussian?
The GW model, again, we are currently timing. It will not be faster. It will be much slower because GW is a non-model based is non-model based, and there we will always. I think that we cannot outpace GW models. For then the statistical applications, you might like testing and so on. You might want to think about model with Gaussian processes.
Thank you. So that were the questions to Jakob. The last ones are to Mikkel Meyer. There's actually only one question, but I also have another one if you have time. Anne Helby Peterson asked, is it possible to create one interface that uses both of your backends, namely Caracas and Ariacas?
Good question. Good question. We actually discussed that already. We decided not to do it. In principle, it is possible, but I'm not sure it would be beneficial. So we decided that the backends are different, and it has different usages. So, for example, the symbols has different S3 classes. So you could do dispatch on them, but we haven't done it, and I'm not. If you have a good application, it would be nice to hear. So then we might do something.
Yeah, may I follow up the question? I didn't think about it, but I think what would be useful is if on the R side you would have just one symbol, and the symbol could be used for Ariacas or Caracas, and both could work with it, right? And then you could.
Yeah, that in an ideal world that's right, but sometimes symbols can sort of signal different things. And would you be able? So if a symbol is a scalar. I could choose that it was a Yaka scalar. Would that be able to multiply that with a SymPy matrix, for example. There are lots of corner cases where you have to think about it and do it correctly. So for now, we decided to separate them and do not work on interaction, because I think it's a lot harder problem than doing it separately. And I think we need some gains to see what we get out of it to do it.
Yeah. I have my own question. I have used Ariakas in the past a little bit. So you concentrate now on Caracas. Is it because you think that the SymPy is really very actively developing and the underlying Yakas is kind of stable but not being developed? Or why did you emphasize on Caracas in your presentation? And you said also in your future work, right?
Yeah. So it's because the engine below it, the SymPy engine, is larger and has more functionality. It does have some drawbacks, as I mentioned, with communicating back and forth to R via reticulate instead of having a really tight interface. But I think that's better because the end users they want to have something where you can solve some advanced system of nonlinear equations and stuff like that, and that's more important for them than a tight integration, I think.
Okay, thank you. Yeah, so I think we are also a little bit up on time now, but thanks to the full audience for asking all the questions on the chat, and thank you very much to all four speakers. I can clap now and being visible, but yeah, thank you very much, all of you. It was very enjoyable, and enjoy lunchtime now. And so I think we close this session being very happy about all of you. Thank you.
Thank you.
Thank you. Bye.
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 Bye. Thank you again. Okay.